Hello. I've been asked to go through a few of the oscilloscopes quiz app questions at level 3. This is the first one I've been asked about. A digital multimeter, an RMS digital multimeter set to AC plus DC mode. Right, the first thing you have to know is that if you set a digital multimeter to AC plus DC mode, then it will give you the true RMS of the signal, including any DC component. So the method of calculating that, you take the waveform, square it, take the average value of that squared waveform, and then take the square root of that mean value. Now, you'll note that you cannot see how big this waveform is because the top of the square wave here goes off the top of the oscilloscope screen. So the first thing we'll need to do, it's often the first thing we try and do when we're seeing a new trace on an oscilloscope, is to adjust the ground reference level and the amplitude so that the waveform fits on the screen. And if I do that, then I can see that the waveform goes from 0, that's ground, the little diamond there, up to 4 divisions higher than ground. And at 100 millivolts per division, that would be 400 millivolts, or 0.4 volts. Well, if I square that waveform, I'll end up with a waveform that goes from 0 squared, or 0, up to 0.4 squared, which is 0.16. The average value of a waveform that oscillates between 0 and, say, AV, average value, that oscillates between 0 and 0.4 squared is just 0 plus 0.4 squared divided by 2. So that's my mean square. Take the square root of that, 0.2828, and that's the answer to this one. Next, this one. Once again, we can't see the bottom of the waveform, so we'll have to adjust, in this case, the ground reference level so that the entire waveform fits on the screen. Now, percentage overshoot. Well, the percentage overshoot is how much further than the final value the waveform gets, expressed as a ratio to the total step size. That's the step size from the initial value to the final value. So the first thing I'll do is I'll adjust the cursors here to measure what the final value is. The final value looks like 40 millivolts. Right, so 40 millivolts is the total step size going from the start to the end. The overshoot is this bit here, how much the waveform goes past its final value here before returning to its final value eventually. And I can measure that in a similar way. That is 17.8 millivolts. Okay, so 17.8 millivolts expressed as a fraction to the total step size would be 0.445, and expressing that as a percentage would just be about 44.5%. Fine. Now this one. Ringing frequency. Well, the ringing frequency is the frequency of the oscillation as one of these step responses settles down to its final value. Difficult to see with this particular time base, so let's change the time base until we can see the oscillation a bit more clearly. Fine. Now, the frequency is 1 over the period. If I move this cursor to there, so it's at the bottom of this oscillation bit here, and the other time constant to the bottom of this trough, then the time between here and here will be 1 period of the oscillation. So the ringing frequency is just 1 divided by the period, so that would be, in this case, about 6.9 kilohertz. And finally, this one. Now, here we can see the whole of the waveform on the screen, but it's only occupying, well, less than one division on the screen. So we're not going to be able to get very accurate results using the cursors. Let's expand the scale a bit, make it bigger. I think that's probably the biggest we can get it and still have it to fit on the screen. Yeah, right. Okay. Now, let's see what its final value is. If I move this amplitude cursor down to the bottom, this amplitude cursor up to the top, I can see that the total height of the step is about 1.5 volts. Now, if the total step is 1.5 volts, then it will reach within 10% of that final value when it gets 90% of the way to 1.5 volts, which is 1.35 volts. So I'm interested in how long it takes to get to that point there, 1.35 volts. Now I can probably get that reading more accurately if I expand the time base a bit. Let's head off to, let's say, 500 microseconds per division. Right, now the time between the start of the waveform, which would be that point there, and the point where it goes through that amplitude level is 2.29 milliseconds. So answer 2.29 milliseconds. That's it. Key point in all of these is change the scales and change the ground reference point so that the trace appears as big as it can on the screen. Then you'll get the most accurate results with your cursors.